First couple of announcements. Chapter 3, question 3.3 was a typo. We fixed it. Likely is not, and we're reminded about this yesterday's discussion, but I thought it's not. I've got a formula in there. This type. Section 3.3 is an exercise in simply assignment of observation numbers based on the rules of the road which are in the notes, on which I reminded you you're expected to learn. And point me reading the rules to you, I'm not going to say anything different. The item containing formula with chlorine is supposed to be ICL5, not ICL5 with a minus charge. Just take away the minus charge. Remember, I announced this last time, we're going to employ a different special quiz format compared to the description of special quiz format that's in the syllabus. I'm changing the format when I post special quiz number 1, which I'll do this weekend. I will include a description of the new format just to make sure we all understand what it's about. I repeat, the new format will be intended to have you be successful on each and every exam, including the final. A change from the originally planned 3 special quizzes to 4 special quizzes. And now each special quiz will be issued at least a week before the coming exam. The rules of the road for dealing with the special quiz will be the same as stated in the syllabus. Any information source is fair. Each other, web, notes, whatever book you might like, or books. Except
us.
the instructional staff members for this gathering or any other professional instructors of chemistry. That's not fair. Now, I will tell you that in dealing with special quizzes in the past, I've had students go to places like Tutoring Zone. That's not what you're supposed to do. And pay money to have these people work out the special quizzes. And I must say, I really enjoyed it when, after having spent this money, they got zeros. Because the people at these places don't know how to deal with the material. In many cases. Particularly if it's presented by yours truly. Because I present stuff that requires you to think. I am never interested in your feedback of a piece of information. That's jeopardy. I don't care about jeopardy. I care about thinking. Any questions that I issue you will always require thought. And of course, this special quiz will contain questions in regard to Chapter 4 on stoichiometry, which we've yet to discuss. So don't get all upset if you see a question or two on the special quiz, which as yet you cannot successfully wrestle with. But hey, if you want to read ahead, the stuff that I'm going to ask you about is all stemming directly from and parallel immediately to what's in the notes. So you can always look at what's in the notes. You always got that for support. And since all discussion gatherings didn't get through this stuff yesterday, I posted a solution key on Canvas for questions 313 through 318. On the Rutherford Act. Remember the Rutherford experiment? Great experiment. The upshot of which was for physicists and chemists to finally have an idea of what an atom actually looks like. This wonderful thing which you can't see, but which is part and parcel, fundamental component, part and parcel of every form of matter. In the main, what does Rutherford find out about atoms from a material distribution standpoint? What? Mostly nothing. 99.99% of an atom is nothing. Nothing! That means as you look at me, 99.99% of what you nothing. Because you, like I, are made of atoms. How about that? That's not a derogatory remark at all. It's just a statement that follows immediately from the Rutherford atom. But of course, when he fired his alpha particles at his gold foil target, to get an idea of what the structure of the atom was like, every now and then, one of the alpha particles, which is a positively charged helium nucleus, came close to the nucleus of a gold atom and it veered off straight line trajectory because of positive repulsion. Nucleus of the gold atom, 79 protons in that thing. So when a +2 helium particle came closer, it was pushed away. And every great once in a while, that alpha particle hit one of those gold atom nuclei right on the nose. Well, here's a particle with an atomic mass of 4, 2 protons, 2 neutrons. That's the helium alpha particle. Hitting this gold nucleus with 79 protons and a whole bunch of neutrons. Because there reported the average atomic mass of gold is 196.967, call it 197. So if you subtract 79 from 197, you know how many neutrons, on average, are in a gold atom nucleus. Well, that's a whole lot more massive particle. So the alpha particle goes, bing, bing! The Rutherford says, ah! Like shooting a cannonball at a piece of kimberlite, and it bounces back at me. But we know why now, don't we? So if you didn't get to that, stuff to see. Now then, continuing from our previous point of departure. Section 3.9. Some comments on these things. Elements, for which you see the symbols in this periodic table, that periodic table, or the periodic table that's included in the ChemNote. At the end of the note package, there's a periodic table for your convenience. From a type standpoint, what kind of elements do we have? Metals, nonmetals, and metalloids. When I glance at the periodic table, which of these elemental types is the most common? Metals. But interestingly enough, most of the important chemistry important to chemists, particularly chemists who study nature and life, stem from what elements? Specifically, which nonmetals? Carbon, hydrogen, oxygen, nitrogen. You betcha. You think nucleic acids are important? Amino acids? Proteins? You betcha. These are the molecules of nature and life. Those composed of those atoms in general. That's why we have a whole year devoted to organic chemistry. Chemistry of those molecules which have carbon as their principal skeletal atom. Over 10 million of these organic molecules now known, and we're making new ones and learning about new ones every day. And over here, in a moment, we'll talk about general properties exhibited by these materials. Now, nonmetals, atomic elements. There's really only one family of atomic elements. That's 8A. Although on this table it's labeled column 18. Never mind the labels. Right-hand most. Atom. Helium, neon, argon, radon. What does it mean to refer to these elements as atomic? Well, they exist as atoms. In any sample of noble gas, regardless of which noble gas it is, do you or do you not find bonding between and among the component atoms of the sample? Not. They exist as individual entities exclusively, and the only kinds of attraction forces among and between these atomic elements are what? I wonder if you heard about it. London forces or Van der Waals forces. You heard about this? And when we get to this, you'll find out that these kinds of forces depend primarily on atomic mass. Molecular elements. Well, we've talked in brief about these previously. Like the noble gases, our molecular elements, for the most part, are labeled with red symbols. But the principal denotation of the red symbol is that that is an element which, under normal laboratory conditions, like the conditions which are here with us in the room, exist in what phase? Gases. That's right. Now, under normal laboratory conditions, there are only two elements which exist as liquids. Do you know what they are? Bromine and mercury. You can see their symbols typed in blue to designate that. The rest of the elements exist as solids under normal laboratory temperature conditions. Now, what's the difference between molecular elements and atomic elements? Molecular elements, the most simple of which is hydrogen, exist as molecules. That's what they call molecular, which means the fundamental component of a sample of elemental hydrogen is an H2 molecule where two hydrogen atoms are glued together by a covalent bond, a shared electron pair. Now, what kind of attraction forces exist in a sample of pure hydrogen among and between the hydrogen molecules? Remember what we said for the noble gas? Atomic elements? London forces. So I've shown a picture of that over here, where this hash line represents these very weak London forces. Well, as compared to the strength of the covalent bond, these are very, very weak. Metallic elements. Principal characteristic is they have mobile valence electrons, which, for a bulk sample of any metallic element, like a piece of copper wire or iron wire, these electrons transfer from atom to atom throughout the sample, which leads to, for most metals, strong, fairly strong bonding. I've already told you the story about if you think iron atoms aren't bound strongly to each other, get yourself an iron hammer and whack yourself in the head. See what gives way, the iron hammer head or your noggin. But don't do the experiment. Of course, this mobile valence electron property leads to conductivity of heat and electricity by metallic elements. Then metalloids. Now, you can't see this very well on this table, but if you look at the table that's in the chem notes, at least I believe the table that's in the chem notes shows you this. Now, you see this heavy black step line that starts vertically to the left of the symbol for boron, then horizontally separating boron from aluminum, and then down separating aluminum from silicon. Most of the elements whose symbols are adjacent to this heavy black step line are metalloids. Aluminum is not a metalloid, but boron and silicon and arsenic and germanium, those are metalloids. And you'd like to guess that these are elements which show properties characteristic of molecular elements, metallic elements, and macromolecular elements. I guess I forgot to write macromolecular up here. Put it over here. Very nice for having left us through this space. There are not many elements which show properties of macromolecules. But carbon is the most obvious prevalent example. What's the difference between a molecular substance and a macromolecular substance? In a bulk sample, go ahead. Didn't hear you. in which, in three-dimensional fashion, you have strong covalent bonds throughout the lattice of the sample. That's carbon diamond. Or has many covalent bonds extending throughout a bulk sample of the material, like carbon graphite. Now, these models are not very good, but that's all we have. This is a model of carbon diamond. The alternating colors, the black and this kind of light brown, is just to assist you in visualization of such. If you wish to imagine you're looking inside a carbon diamond lattice, what will you see? You'll see an arrangement of carbon atoms like this. You'll see that every carbon atom is tetrahedrally surrounded by 4 nearest neighbor carbon atoms. And if you want to look at these models more closely after our talk, come up and take a look. That's what I'm doing. We'll talk extensively about this stuff later on when we talk about the covalent bond itself and its significance in maintaining structural integrity for materials. But in carbon diamond, we find, as we said, every carbon atom in the sample, in one chunk of carbon diamond, is covalently connected to every other carbon atom in that sample. Well, these covalent bonds are very strong. Do you think that accounts for why carbon diamond is very hard? Can be used as abrasive material, has a melting point that, woo! Big time. Interestingly enough, although carbon diamond is an electric insulator, it happens to be a marvelous heat conductor. More about that in the future. Now, to draw a comparison for a different kind of macromolecular substance, where there's an extensive pattern of covalent bonds, but it doesn't proceed throughout the sample. Here's carbon graphite. Now, if I hold the carbon graphite model like this, and I point at any single carbon atom in the graphite lattice, you'll see that a carbon atom in graphite is covalently connected to 3 nearest neighbor carbon atoms. Whereas, again, in the diamond lattice, a carbon atom is covalently connected to 4 nearest neighbor carbon atoms in a tetrahedral pattern. Here, a carbon atom is in a trigonal planar pattern of carbon atoms, with 3 nearest neighbor carbon atoms. I'll ask the question. Right now, this is just for fun. Do you think the carbon-carbon covalent bonds in graphite are stronger than the carbon-carbon covalent bonds in diamond? No. Do you think the carbon-carbon covalent bonds in diamond are stronger than the carbon-carbon covalent bonds in graphite? Yes. Okay. Everybody voted wrong, but that's okay. That's fine. This lays foundation for stuff going to in the future. We will discover that the carbon-carbon covalent bond connections in graphite are considerably stronger than the carbon-carbon covalent bond connections in diamond. Now, I expect that you offered your response on the basis that if you take a carbon graphite pencil, and many of you may well be using this, you can scrawl notes with it. Do you think when you write notes with a carbon graphite pencil that you're tearing apart carbon-carbon bonds? You are not. Not at all. Now, of course, if you wrote with a carbon diamond pencil, your notes would be a collection of scratches. You tear holes in the paper or the desktop. Then the UF police would come after you. I'd say, that's no problem. They just write chemistry notes. It's okay. Tell the police to go away. But if I hold the graphite lattice like this, notice when I hold the lattice like, when I hold the sample like this, for the model, I hold the model like this, you see the shortness between carbon atoms? Now when I hold the model like this, you see this long connection between the carbon atoms? Because these covalent bonds, which extend throughout the graphite lattice, extend only through a plane of atoms. Like all the carbon atoms in this plane are strongly connected to each other. All the carbon atoms in this plane are strongly connected to each other. All the carbon atoms in this plane are strongly connected to each other. But all the carbon atoms in this plane are only weakly connected to the carbon atoms in this plane. So guess what you're doing when you write with a graphite pencil? You're leaving behind a smear of carbon graphite where the atoms are connected to each other as a consequence of having been with each other in the same plane. But tearing these bonds apart, that's weak. Because these are not formal covalent bonds. What kind of bond do you think these are? London forces, these weak van der Waals things. And they're much weaker than covalent bonds. That's what you tear apart when you write with a graphite pencil. More on this stuff later. Oh, I should also mention, even though again you likely won't understand this now, that's to be expected, that's fine. Graphite is a pretty good conductor of electricity, but not diamond. That's a non-conductor of electricity. The one word which explains and accounts for the electrical conductivity of graphite is, does anybody know the word? It's called R-E-S-O-N. Resonance. Resonance and resonance, you betcha. Valence electrons can travel from end to end of a plane of carbon atoms in the graphite lattice, accounting for why this stuff is electrically conductive. More on that later. Reactivity of elements. Few comments. 1A metals. You know anything about the reactivity of 1A metals? They're daggone reactive. Main reason is?
They need an electron to fill their purpose.
That's okay, you should respond.
They only have one left to lose before they are.
They only have one electron to lose in order to achieve NGS. You know what NGS is? Noble gas structure. Remember these atomic elements? Very unreactive, very peaceful. And from an electron configuration standpoint, the main reason why atoms react as they react is to become peaceful and stable. And how is that achieved? By developing noble gas electron structure. And when these 1A metal atoms lose this one electron per atom, they get this noble gas electron structure. And in so doing, they become quite peaceful and unreactive. Remember our story about sodium versus sodium ion? In the sodium ion, sodium tongue test? You don't want to do that tongue test. Sodium ion is okay. Don't try it with sodium. Because if you do, and you have a fairly substantial size amount of sodium, you'll only do the tongue test once. And I don't think you'll complete the test. We will stand and say, no teeth, no mouth, did the sodium tongue test. On we go. 2A metals. These are reactive, but less so than 1A metals. Well, the main reason is, for the 2A metals to achieve noble gas structure, they have to lose how many valence electrons? 2. That costs more energy to lose 2 electrons rather than 1. Now, 8A nonmetals. We've already mentioned those. They're quite inert. What's inert mean? Unreactive, peaceful, stable. Why? Hey, they already had. And what's the significance of noble gas structure? It's very stable. You betcha. On the other hand, when we go to the neighboring collection of non-metal atoms next to the noble gas atom, the halogen atoms, fluorine, chlorine, bromine, iodine, and radioactive astatine, they're quite reactive as well, especially fluorine. I think it's fair to state that fluorine is the most reactive of all atoms. How many valence electrons does a fluorine atom have to exchange to become noble gas structure? 1 or 7. Because if it loses 7, it would be isoelectronic with helium. What's that word mean, isoelectronic? Of the same electron configuration. That's what isoelectronic means. You're not going to read this now. It was all written out when you're responsible for it. Well, we're laying foundation right now for when we talk about electron configuration. Because we will be able to relate reactivity to electron configuration. That's what we're really doing now. Install. One more comment. It's up here. If I survey the reactivity of the 2A metals, I'll see that the reactivity increases as I go from top to bottom inside the family. Beryllium is the least reactive, and discounting radium, because of its radioactive nature, barium is the most reactive. But if I look at the reactivity of the halogens, that reactivity decreases as I go down the family. Fluorine is the most reactive, by far, of the halogen elements, whereas, as we've already said, barium is the most reactive of the 2A metals. Any idea why?
For the 2A metals, they have many layers of electrons shielding the valence electron from the nucleus, so it's easier to lose valence electrons. Whereas for the halogens,
All right, let's stop with the metals, okay, and then we'll talk about halogens. That's good what you said. In the main, the reactivity of a metal atom is directly proportional to its size. The bigger the metal atom, the more reactive it is. Because metal atoms characteristically react by losing electrons to achieve noble gas structure. So when I look at the reactivity of barium compared to beryllium, I see this big barium atom next to this small beryllium atom. And what I recognize, and we'll talk extensively about this at the appropriate time, valence electrons are much easier to remove from barium than from beryllium, because the barium atom is much larger, and we have all these collections of inside electrons called core electrons, which shield the outside valence electrons from nuclear attraction. And the more effectively these valence electrons are shielded, that means prevented from feeling the attraction of the nuclear protons, the more easily they are lost. It's all more reactive as they go from top to bottom in a collection of metallic elements. Ha! But there's a different game going on with the non-metal atoms. Why is that? Do the non-metal atoms characteristically react by losing electrons? No, they react by gaining electrons. So I should expect fluorine, the atom, to gain electrons more readily than iodine. So now I got the small fluorine atom and this big iodine atom. And what we'll find out is that when it comes to electron addition, the closer the added electron can get to the nucleus of the atom to which it adds, the more readily it adds. Because it's that nuclear attraction which stabilizes these electrons. So that fluorine nucleus, even though it's only got 9 protons in it, attracts electrons a whole lot more strongly than the iodine nucleus with 53 electrons. Remember all that shielding stuff we talked about with the metal atoms? Well, heck, all those inside electrons for iodine, they're shielding the addition of an electron. But not for fluorine. It has very few shielding electrons. So in pops this electron as fluorine reacts explosively to become the fluoride atom. More on that stuff later. All right. Compound types, ionic, molecular. Hey, I mean in general. In general, all compounds are ionic or molecular. A couple of exceptions. We're not going to worry about the exceptions. Let's talk about the vast majority of compounds. Ionic, thousands and thousands now known. Molecular, over 10 million now known. As I said, we're learning about new ones every day. In the notes,
may I ask a somewhat silly question?
the silliest question is the one you don't ask. Go on.
Since all of this is so incomprehensibly small and we can't actually see any of what's going on, how is it that we know what these molecular structures are and like the levels of electrons?
Why don't you wait till we get there? We'll answer your question. I don't want to stray away from the present presentation and go into that now, since we're going to do it. That's a fair question.
It is a good.
Now, on molecular elements before I wrote those on ionic, not elements of compounds. I meant to write those for ionic compounds first because the molecular elements compounds are in far greater abundance. Okay? So ionic first. If I wish to find out if a compound is ionic or molecular by observation, then I need to be familiar with the physical properties exhibited by each of these types of compounds. Nothing fancy about this thing. Ionic compounds are all characteristically quite crystalline. It means they have distinct shape and structure. Some crystals are needle-like, cubic shaped, beautiful shapes, diamond shapes. What a distinct shape exhibited by all these crystalline materials. They're quite conductive as a melt, because these ions now, component ion particles of the sample being removed. They have high melting point if heating does not cause decomposition. But here's a reminder to you. Ionic compounds with polyatomic anions commonly decompose on strong heating. What's a polyatomic anion? What's polyatomic mean? We're talking about an anion was composed of more than one atom, no more, no less. Like carbonate ion or nitrate ion or sulfate ion. Example presented in a moment. And ammonium ion compounds. All ammonium ion compounds will decompose on strong heat. Why is that? Well, let's take a look at a couple of examples. Sodium chloride. A simple binary compound. Binary. Composed of two different elements only. If I heat this strongly, I will get sodium chloride liquid. I will have a material which is quite conductive. And I'll observe a melting point of 800 degrees centigrade. Stuff on that. But if I take calcium carbonate, this stuff that I hold before you, teacher's favorite weapon, mainly calcium carbonate. If I try to melt this stuff, it will refuse melting. It will instead decompose. And in so doing, it will become calcium oxide and carbon dioxide gas. But the temperature to achieve this is fairly high. And when I turn calcium carbonate into calcium oxide, now I'm going to have a material which can be melted, just for fun. How do you think the melting point of calcium oxide, this stuff, compares to the melting point of sodium chloride, which I told you was about 800 centigrade? How do you think the melting point of this compares to 800 centigrade? I think it's about the same, higher or lower. That's the three bets. I don't care about bets. I don't care about explanation. How many go higher? How many go a whole lot higher? All right? A whole lot higher is correct. Why? Well, we're not transferring any electron when we melt ionic compound. This stuff is composed of Na plus and Cl minus particles. So the structural integrity of a sodium chloride ionic lattice is maintained by stickiness between sodium ions and chloride ions. But in this, the structural integrity is maintained by stickiness between calcium ions and oxide ions. Do you think these have a stronger tendency to stick to each other than these do? Yes. Isn't this twice as plus as this? Yes. Isn't this twice as minus as this? Yes. That's right. Enough on that for now. Now what about these heating ammonium compounds? You folks will go to 46 laboratory next year, where most if not all of you will do this experiment. You'll find out that all ammonium ion compounds decompose on some type of strong heating, so you won't find any melting points tabulated for ammonium ion compounds. Why? Because when I heat this stuff strongly, in my attempt to melt, I will force ammonium ion to behave as a Bronsted acid, and in so doing lose H+. Transferred to this Bronsted-based chloride ion. Remember this ionic compound. Both ammonium ions and chloride ions. When I heat this strongly, I'm going to drive H+ from this and cause it to bond to this. Not surprising, since these are in intimate contact with each other in the sample of ammonium chloride itself. Well, that gives me hydrogen chloride gas and ammonia gas. These are volatile materials. Gases, right? So they go away. That's how this stuff decomposes. You'll find out that if you put a sample of this in a crucible and heat it strongly for not a very long period of time, and look back in the crucible, there's nothing left. Because all this stuff left. But when you do this, there's my Van Gogh sketch of a Bunsen burner, heating a crucible, ammonium chloride in there. If you want any of this, any of you want this picture signed, your art collection, fine. You will see when you do this, that above this crucible, you'll see particulate matter above the crucible. And then, in a short time, you'll see no longer the formation of particulate matter. And then you look back in the crucible, you see no ammonium chloride left, no crystalline solid left. So what's that particulate stuff? Any idea? You think these two materials have a strong tendency to react with each other? Do you remember us talking about hydrogen chloride? If you dissolve it in water, it reacts 100%. Well, let me make a statement to you. Hydrogen chloride reacts with water to an extent of 100% because hydrogen chloride is a strong Bronsted acid, and water is a strong enough Bronsted base to extract all those H pluses from the HCl molecules with which it meets. This stuff, and you're going to do this in lab, is a stronger, much stronger Bronsted base than water. So do you think then if this is a much stronger Bronsted base than water, this has a much greater tendency to grab H plus than water? Yeah. You betcha. And what happens when this grabs H plus in this reaction? What do you make? You make ammonium ion and chloride ion. So what you see here is ammonium chloride at reform. The right side. These gases leave the crucible. They cool down. They're getting away from the source of heat. When they cool down, they slow down. They bump into each other. And now, because they have lower kinetic energy, they bond, interact, and they interact with each other so as to transfer back H plus from this to this, to regenerate ammonium ion and chloride ion, and white crystalline solid ammonium chloride reforms. That's what's going on there. Now then, how about molecular products? What physical appearance may I expect in general to be exhibited by molecular compounds? Well, let's not get into the acid-base chemistry any further. Do I know molecular compounds which under normal laboratory conditions are gases? Well, we just talked about one. Actually, we just talked about two. These materials are each gases under normal laboratory conditions. So if I am issued a sample of material and I'm told that it's a pure material, and I find out that physically it's a gas, I know it's not ionic. How about liquid? I'd say we're all rather familiar with this stuff. Now tell me, under normal laboratory conditions, is the only stable phase of water liquid? under normal laboratory conditions, is the only stable phase of water liquid. Well, what's the other stable phase? Gas. You believe there's water vapor in here? You believe this room has a measurable relative humidity? You believe I'm sweating? You believe some of that perspiration is evaporating? You believe that leads to cooling me? Because in order to convert liquid to vapor, the liquid has to absorb heat. And if the liquid on my surface, commonly referred to as perspiration or sweat, absorbs heat from me to convert it from liquid to vapor, I can cool up. And of course, solid. And regarding solid, it will be crystalline or amorphous. Give me an example of a crystalline solid that's molecular. Silicon's an element. When a molecular compound, which under normal laboratory conditions is a crystalline solid, and I want a material with which you are familiar. Quartz. Quartz is macromolecular. Calcium carbonate. Is that what you said? It's ionic. That's element. I want a molecular compound with which you are familiar, that under normal laboratory conditions is a crystalline solid. How about table sugar? And we've already commented about this being an ugly formula. This tells you nothing about the structure of this stuff. But a simpler sugar is glucose. Composition formula C6H12O6, and you'll see a structural representation of glucose in the notes. We're going to be talking about that in a moment. In any case, how about amorphous? Are you familiar with any amorphous solids which are molecular compounds? Remember this picture I drew over here? This picture really looked like a Bunsen burner? What's this picture look more like? Candle! What's candle made of? How about it? Now, if these materials each melt without decomposition, which do you think will have the much higher melting point? The molecular crystalline solid or the molecular amorphous solid? Crystalline why? You think it has much more stable structure? You betcha. The intermolecular attraction forces in the crystalline solids, which are molecular, are considerably stronger than the intermolecular attraction forces in amorphous solids. Why do you think the intermolecular attraction forces in table sugar are quite strong? What are these intermolecular attraction forces? They have a name. What are they called? They're called hydrogen bonds. Have you heard about that? How about that? Now then. One last peek. And I saw. You'll see a picture of this in the notes. Let's see. Page 316 at the bottom. I want to take a look at this right now, so I don't have to bring them out of that. This is a model of the sodium chloride crystal lattice. Blue spheres surrounded by orange spheres. This is a Gator sodium chloride. Do you think the blue sphere symbolically represents the sodium ion and the sodium chloride lattice or the chloride ion? Blue sphere. How many vote sodium ion? How many vote chloride ion? More votes for sodium ion, but a lot for chloride ion. Is the orange sphere sodium ion and chloride ion? How many vote sodium ion? And if you vote twice in this game, something's wrong. Oh, not really. Chloride ion. Well, then, if the chloride ion votes for this being chloride ion are correct, that means chloride ion is a lot bigger than sodium ion. Do you think chloride ion is a lot bigger than sodium ion? Remember, when I make a cation, when I take a sodium atom and remove from it an electron, what have I done? I reduced the degree of electron-electron repulsion among the remaining electrons, right? Because I took away electrons. And I magnified nuclear attraction because now the proton to electron ratio is greater than 1 to 1. But when I take an atom and give it an electron, like an electron to chlorine turned into chloride ion, now I've increased the degree of electron-electron repulsions in the electron cloud because I had an electron in there. And I now have a proton to electron ratio which is smaller than 1 to 1. So now the average nuclear attraction per electron is less than it was for the parent atom. Upshot, when I take an atom and take an electron away from it, I shrink it. But when I take an atom and give an electron to it, ooh, I expand it. We'll pick it up on this point next time.